We're in Rosen Discrete Mathematics and its Applications, section 1.8. And in this discussion, we will talk about existence proofs, counterexamples, and uniqueness proofs. With existence proofs, there's two types. And one of those types is, well, for existence, we need to show that there exists x such that p of x. That means we need to find at least one x in the domain that makes p of x true. And for a constructive existence proofs, this is one of the types of existence proofs, we will actually find a c for which p of c is true, and then we can say that there exists x p of x by existential generalization. Here's an example. Show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. One way to show that this is true would be to find one. And, well, here's one. 1729 is equal to 10 cubed plus 9 cubed, and it is also equal to 12 cubed plus 1 cubed. There are actually many more of these. The interesting thing about this number is it is the smallest integer that can be written as the sum of two different cubes in two different ways. Sum of cubes in two different ways. The relation of these two famous mathematicians to this number, I will let you discover on your own, but it has to do with the fact that these numbers are called the taxicab numbers. All right, so that is constructive existence proofs. Let's look at the other type, non-constructive existence proofs. In this case, we will not find a C which makes P of C true, but we will show that it must exist. All right, here's our example. We want to show that there are two irrational numbers, x and y, such that x raised to the y power is rational. Okay, well, we know that square root of 2 is rational from earlier discussions. Let's consider the number square root of 2 raised to the square root of 2 power. Now, if that number is rational, we've found a solution that two irrational numbers, one raised to the other power, would be rational. On the other hand, if it is irrational, we can raise that number. We'll say that x is equal to that value. We'll continue to have y be square root of 2 so that the square root of 2 raised to the square root of 2 itself raised to the square root of 2 equals the square root of 2 squared, which is, of course, 2. So if square root of 2 raised to the square root of 2 is rational, we're done. If it is irrational, then it is also it would be an example of an irrational number raised to an irrational power. The question is, which of these is true? Well, I will tell you that the square root of 2 raised to the square root of 2 power is irrational, but the proof of that is outside the scope of this course. However, we can prove that a solution to this does exist. We just don't know what it is because we can't, from what we know right now, tell which one is irrational. For counterexamples, you will have learned that this equivalence is true. There exists x such that it is not the case p of x is the same as it is not the case that every x p of x. So if we want to try to prove something that is of that form, that is not the case that for every x p of x, or we want to show that for every x p of x is false, then we need to find c such that it is not the case p of c is true, or equivalently that p of c is false. This case C would be called a counterexample to the assertion that for every x, p of x. Here's an example. If I wanted to assert that every positive integer is the sum of the squares of 3 integers, I can find a counterexample in 7. 7 is not the sum of 3 squared integers. You could try all possible combinations of the sum of the squares of 1, 2, and 3, and 4, and clearly you're not going to find one that equals 7. So 7 would be a counterexample to that claim. Okay, uniqueness proofs. Oops, I forgot to do a build on my arrow down there, or triangle. Okay, so uniqueness proofs. In this case, we want to show that there is a unique or one and only one element that makes my proposition true. There exists a unique x, p of x. In order to prove these, we have to show that a solution exists and that the solution is unique. Here's an example. If a and b are real numbers and a is non-zero, then we say that there is a unique real number r such that a times r plus b equals 0. And we can find that real number using algebra, or find a solution using algebra that r equal to b is equal to negative b divided by a solves it, because when we plug negative b divided by a in for r, we get an equality. We get 0 equal to 0. Is that the only solution? Well, we can show that it is, because we will assume that there is a different solution such that as plus b equals 0. But in that case, ar plus b will equal to 0, which will equal to as plus b. And then we can subtract b from both sides and divide by a, showing that r is equal to s. So we showed that r equal negative b over a is a solution, and that every other solution would be equal to r.